So today I'd like to talk about, so the goal is to get to the fourth bullet, data and model poisoning, right? But to get to the fourth bullet, I have to do the other three bullets. And so I have to, give a foundational piece, right? And then how it's trained, the LLM, and then talk about the different configurations, right? And then we'll get into data and model poisoning. And then we'll talk about supply chain risks. Can you see it okay? It's probably a little small. So this is the LLM life cycle, development life cycle, right? So at the far left, you have data collection and preparation. So you need to get all the data that you want to use to feed this model. Data pre-processing, we have to make sure that the data is as clean as it can be, right? And we have to know the sources of where that data comes from. That could be an extensive process to train these. It is very important because that data is going to be the data that's going to set the path for this LLM potentially for years, right? So we want to make sure that that's absolutely pristine. Then we have the model development. There's still software development that has to happen, right? We feed it data, but we have to do something with that data. We have to have code in there that actually operates the whole thing. And so then we have model training, which we'll talk about today. That's where the model learns language. That's where the model learns how to interpret context, right? Evaluation and validation. Always have testing and validation in the life cycle. Deployment, and then monitoring and maintenance. And this isn't like your traditional monitoring and maintenance. You're looking not only for, capacity and making sure that it's, has enough headroom to operate and isn't slow and this and that. You're also monitoring for bias, right? And other things that can creep in. And so you have to there's separate tools and all this and that. There's approaches to do that. But you want to make sure that you monitor this a little differently because it's an active generative LLM, right? So when you're developing software, so standard software is, human-defined instructions, very clear data structure. LLMs are data-driven at their core. And so they're trained on massive data sets of text and code. So a lot of times they will use code as another training component because it has good structure, right? And so that helps the model. Also, it could be books, it could be whatever. And so it wants to learn language, it has to learn patterns and so forth. And then, and we'll talk about that in a minute, about how it then gets to be more context-oriented. Standard software, once developed, remains static, right? But LLMs can continuously improve with the feedback. So it will adapt to some degree. Whenever you hit that thumbs up button, thumbs down button, you're helping to train the model a little bit, right? That's the continuous improvement or continuous learning. Okay, so to understand security in the model, we have to understand this piece. And so this is the neural network of the model, right? This is kind of the core. And so these networks have been around. So they've used recurrent neural networks, which are RNNs. And however, they had a problem. They couldn't keep context for long periods of time, right? Because if you want to load up a book or you want to work on this thing for hours, like I do, I work on it for hours. Sometimes it says, stop, go to bed or whatever. Last night it cut me off, said you can only come back on in 2 hours. So, there's long-term context that has to be maintained. And these networks couldn't do it, the RNNs. And so they had this, what they call the vanishing gradient problem. All right, I'm not going to go into it. So before I leave, in these networks, you have a neuron, right? A neuron is this little, thing here. A neuron, for lack of detail, think of it as a gate or a switch, right? Very rudimentary. I'm oversimplifying it dramatically. But so imagine, this is a switch, it's open and wants to go to this direction, it's open and wants to go back up to this direction. This is the layer of neurons. So when they talk about layers, we're talking about this, right? And as information comes in, not all neurons will fire. Some may fire and because they have the parameter set to open the gate, right? Some won't fire because their parameters are set to not take that word or that element, right? So these are a series of switches on and off, and they're pushing information through. This is called a feed-forward network, right? They're pushing it through. And it takes numerical data, right? And it only operates in that world. This is in red, parameters. So you have to understand what a parameter is to get down to the security component. Is this loud enough? Can everybody see?
I think people on Zoom cannot.
Yeah, I did. Yeah. So, so that was the original LLMs, and it didn't do very well. So in 2017, Google wrote a paper, Attention is All You Need. I don't know if any of you are familiar with that, but that was the big breakthrough that they had to get to this current class of LLMs. And basically added in this notion of attention. And so as you see, they're still using the feed-forward network, the neural network, but they have layered embed, or they have layered in between it, they have layered other arrays and vectors to do different things. We'll talk about that in a second. So the way this works, some of you may be familiar already, is user puts in something, right? In this case, they put in the cat is. And so out the other side, they have to know or try to guess what that is, right? So it comes in, it's tokenized, right? It has to be prepped in a way so that, the software, from there on out can interpret it, right? And so they tokenize it. They primarily are looking for, keywords. The and is may not be used, but cat will be something that's used. Now remember, this is in the middle of a series of sentences or a paragraph, right? So it doesn't just have this and says, oh, I know what the answer to that is. No, it's looking at the context of your thread that you're using, right? Like, for example, yesterday I was showing somebody and I said, draw me a picture of a, yellow tabby cat. And it did that for me. In fact, it gave me two. I could pick which one I wanted, ChatGPT. And then I said, write me a story. Well, guess what? It wrote a story of an orange cat called Oliver. So it's keeping that context, right? So then it's what they call embedded. And so they put it through a series of multidimensional, they call it multidimensional spaces. It's just a series of vectors, right? And it's beginning to orient itself as to where this word should be placed. So then we go into what's called self-attention. And so this is looking at the word itself in the context of the sentence. So if you have a longer sentence, it's going to take all those key words and it's going to try to figure out, okay, what does this whole sentence kind of mean, and what's the order of all these words in the sentence? That's the first pass, and that helps with the initial orientation of the word. So then we go into multi-headed attention, right? So now we get serious about finding out the real essence of this word. They use the term essence of the word, because if you think about it, a word has a lot of meanings to it. Horse could be, a big horse, a small horse, a pony, a draft horse. Could be a lot of things. So it's hitting this word from so many different perspectives, right? It's trying to figure out really the essence of the word. And then in the multi-head attention, it begins to take all these individual words and now put them together. I call it a super embedding, right? And so now it's putting all these words together with all this rich information about these words and the context. And so now it's breaking it down to really understand what you're trying to ask, what you're trying to say. And as it does that, then it begins to formulate, okay, I at a deep level, I begin to understand what somebody's asking me. And all through this, we're using the neural network. And so then they'll use multi-head attention, and then that goes into the neural network, and then that goes into other things. And so that's self-attention and multi-headed attention, and the feed-forward network, where the feed-forward network is the neural network. And then we hit the output prediction. Typically, you'll see it called the softmax. And so now it begins to spit out words at you. It's going to spit them out one at a time, but it has the whole context of what's going on. And so, I mean, this is massive, right? You can put a book into this. I'm sure a lot of you have used ChatGPT, load up documents. I've loaded, 5, 10 documents at a time, worked on it for hours, created documents. So it has, a lot of capacity. So one thing I don't know if I talked about yet. Well, yeah, I'll talk about it here next. So the cat is, based on the context, black. That's what we come out with. It predicted the right word. So language training, right? So the neural network is where the language is trained, right? So it has to understand at a deep level, and when they talk about neural networks, they talk about a deep level, all the components of the language, right? And so the language training is a key component of the language training is called the forward pass and the back propagation, right? The forward pass processes unlabeled and labeled data, which we'll talk about in a second. Labeled data is paired data, meaning the answer is part of the process, right? It knows the answer and it tries to get to that answer. That's labeled data. And so it does this and it tries to predict the next word in the chain. Back propagation is a feedback loop in some ways. It basically, as they're predicting going forward, they don't predict correctly all the time, right? It just doesn't work. And so they have to dial that in, right? And so the backward propagation comes back and helps to dial that in. So let me take a step back. So just to clarify something back here. I think I missed it. So at this point here, just to better help understand these neural network and the attention, if everybody could think of, I'm going to say a word, 2 words, and then I want you to kind of get a mental picture. Horse, right? Mental picture. Clown, right? Mental picture. Now, horse clown. Did you feel a second in there where you had to think, what the hell's a horse clown? Is it a picture of a clown on a horse? Is it a clown? Is it a horse with a clown outfit? Right? So, horse, clown, horse clown, right? Think of this as deep learning, long-term learning of individual structure of words. And then this is where you can actively begin to manipulate and create new short-term components, right? So this has a lot of fundamental flexibility to it. Let's see. So go forward. Okay, so to explain how this works, the forward pass and the back propagation, I created the little game. Well, me and Gemini created the game. After like 4 tries, it finally gave me one that I liked. So this is what I call it's a telephone game. Everybody familiar with the telephone game? You try to pass a secret among people. You put in a secret or a word, a sentence here, and it comes out incorrect on the other side. Happens all the time. So here in this game, the goal is to have all these neurons turn purple, right? The goal is, and purple means that it's ready to go. It's got all its parameter, it's really dialed in, right? That one neuron is dialed in. We want to get all those neurons purple, right? This guy here, the first layer, knows the word, so that's dialed in, right? And so the way this game is played, child 1 receives the target word, right, the answer, and generates 3 clues. And he passes not the word, but he passes just the clues forward, right? And so child 2 gets those 3 clues and he guesses, right? So there's 4 components now. So 3 clues and a guess. And he passes the 3 clues and the guess forward, right? That looks at it and says, okay, I got 3 clues and a guess. I'm going to guess too, right? So everybody's guessing. And so then he passes all that to child 4. He's got 3 clues, 2 guesses, and he says, this is my final guess. I get the final guess. And so he puts the word out, and then is it the correct word, right? So far, everybody? Okay. So it's going to be the incorrect word, right? And the teacher's assessment is over here. So the teacher is looking at this and saying, well, we have full purple on the left. That one's dialed in. But these others have, various shades of purple. So they're off. They're off. And the teacher can assess how far everybody's off. So they go and talk to somebody and they say, okay, what was your clue? What was this? And some people could have just took a left turn and some people could just be pretty close, right? So the teacher's job is to come back in and help these 2 components, right? Or these 3 neurons. These 3 neurons are these 3 children with clues. And then they start all over again, right? And they run it down. And did they get better, right? So this one here is, pretty close, maybe 80%. This one here wasn't, but this could go to 80%. This could go to 90%, right? Just keeps doing that until we have all purple, right? And so this is how the model learns language, right? The fundamental component of the whole thing. And it's learning words, vocabulary, syntax, semantics, everything, right? Out of this mass amount of data, right? It's looking at it and trying to figure out patterns and code too, right? So one thing to keep in mind is, and by the way, the word was horse, and it finally figured out the word came through as horse, right? And so one thing you have to remember is that LLMs don't have a database, right? They don't get the prompt and say, oh, let me go look it up and do this, whatever, and then come back. They don't do that. This is the de facto database. When they're done, this neural network has all the structure of the language in it to draw from immediately, right? Because obviously, many of you put in, a sentence into ChatGPT, spits a ton of stuff back at you very quickly, just going through all this whole process at a very fast pace. Now, just to give you a sense of these parameters, you probably have heard ChatGPT comes out with 175 billion parameters, and that's good. 4 comes out with who knows what. And so the more parameters you have, the richer the information that you can glean from the input and that you can put out to the end user, right? So parameters are good, but you can be sloppy with parameters, right? These could not necessarily be fully dialed in or whatever. And so you see Gemini Pro version has 20 billion parameters. And Google's taking a different path than Chat GPT or OpenAI. They're taking a more measured approach. I don't know if anybody in here has used Gemini. Yeah, frustrates the hell out of me sometimes. It really is. It requires you to be more precise, right? And it's kind of built around, they're targeting engineering and science and this and that. And so they're looking for the user to be much more precise. ChatGPT, you put in a word and it spits you back like a page of information, right? So they're built differently for different purposes. Make sense? Okay. Okay, so now we're talking about the training component. And so the way you train these LLMs is first, like we talked about, you have to train them on massive amounts of data to understand language. And this is what they call unsupervised training. And so unsupervised training means that it doesn't know the answer. It doesn't know the target word that we just got done, showing in that example. It doesn't know the target word through the forward pass and the backward propagation. It's very difficult to do the backward propagation because it doesn't understand the target word. So this is a much harder endeavor at this point, right? And so a good one is Wikipedia is a great source of good information, a massive amount of information. Books, scientific journals, all that are just pulled into this thing. And so, as you can see, lazy the over-jump fox, brown, quick the dog. Makes no sense on the training, but as it pulls in all this information, it can begin to say, the quick brown fox jumps over the lazy dog, right? Very common term used, and it's probably all over the internet, and so it could pick that out. The next phase is called fine-tuning, right? It's called supervised tuning. Supervised tuning has the answer with it. So the database here has the answer. And so this is, they want that answer, that specific answer. And so they put in what they call the pair. And so this is a sentiment training, right? Sentiment training means I have a really bad headache, right? Bad headache, sentiment, probably not good, right? It comes out and says, I'm sorry to hear that. How can I help, right? You probably have experiences with ChatGPT, Gemini Pro. Boy, my self-esteem just is wonderful when I'm done. It just is like, you're such a great person, all this, it just really lays it on thick. And I noticed it after a while. It's like, wow, I feel really good, So it's very powerful, and you have to keep that in the back of your mind. And then then at this point, you have reinforced learning from human feedback. And so in this case, I have a medical professional group is in there, nurses, doctors, whatever, and they're the reinforcement learning. And so they put in a diagnosis or a complaint or whatever you want to call it, a concern. 45-year-old male has pain shooting his left arm. The nurse over here would say, okay, that sounds like a heart attack. That sounds like a heart attack. I want to see a heart attack answer. And then it's released into production. And if you guys ever hit that, you're giving more feedback to it. Good so far? Okay, finally got to the heart of the matter here, data poisoning. So as you can see, there's a lot of data being fed to this thing. So data poisoning, if you were to screw up that data some way, shape, or form, that data is used to set those neurons, to set those connections, those parameters, right? Establish those. So if you put in the data, a cat, and you say it's a dog, well, guess what? It's going to make those connections incorrect, right? And so you want to be careful. So somebody who is malicious could come in and do things like that. So if you have poisoned data, then you have a poisoned model because that data is creating that model in the end, right? So types of data poisoning, right? So you see in the fine tuning, you have labels, right? You have the answer and you have, the question to the answer. And so if you begin to flip those labels, the wrong answers are given to the questions. And so they call that label flipping. Bias attack. And so a bias attack would, somebody would come in and craft the data a certain way. They wanted to lean heavily on something in particular. Could be politics, it could be misinformation, whatever. They just want to push that data a little bit. That may be not noticeable, right? That's very subtle in that case. And then you could have a backdoor attack. There's other attacks, but I just want to go through these three. And so you could put code into the database or the data, and it could train on that code, right? You know that. But you could have in there some code that was planted by somebody else. And so when this thing is released into production, a user can come in and, put the trigger, the known trigger to execute that code in the model. And then that code could do anything. It could, flood with information. It could, skew the parameters, right? It could skew the parameters. It could do a lot of different things, steal data, other things. And this can be very hard to find, right? So this could be out there for a long period of time before anybody notices it. Can we wait just a minute? Okay, thank you. So training configurations. So the entire training process is conducted on a single machine for local training, right? This is local training. And this is typically the way it is done currently, like OpenAI would probably do it this way. Google would probably do it this way. You have full control of everything, right? But then there's also federated training. And federated training means that you have different groups trying to create a shared model. You can imagine different hospitals want to share their data, right? They want to get a really robust model, and part of the game is they have to contribute their long-term patient history. Obviously it's mass and all that stuff, but there's needs to do this type of thing. So each hospital wants to have their privacy, right? But they still want that shared model because it's so valuable to the hospitals. So that would be a decentralized or federated. So decentralized is, I don't know if anybody's familiar with blockchain, but it's kind of a decentralized model also. And so you have these multiple elements out there that are just sending the model parameters to other peers out there. And so, so typically this is only done at the fine-tuning stage. It's not done at the core language stage because everybody starts with a base model. Everybody starts with that system that knows language. Now you just want to fine-tune it to the medical work that you're doing, as an example. So, and so the way this can work, it could be very flexible. Same with the federated. So not everybody has to update, send in their parameters, right, at the same time. They could batch them in. You could have people that do it every 5 times. Everybody else does it every time or whatever. So there's a lot of flexibility on how this can work. And you can even imagine someday a service, where people would attach their model and they would get trained in a certain vertical. Say I want to do a medical, I come to this service and it does medical for me. I want to do this, I go to that service, right? And so there's benefit and risk. So you have the data privacy, right? Hospitals are separated with their data. One of the risks is it transmits the model updates through an outside network. So you're now pushing the model out over a network, and it has a standard security concerns there. And you're also relying on the security of all your other partners in the network, right? Because if you have a malicious actor in their system, that propagates over to you because you're sharing that model. All right, I think I can do it. So the point of model poisoning is to manipulate the neural network parameters. Remember we talked about that? It wants to get in at that deep level and manipulate at that point. And it does it through manipulating the weights, right? The parameters that determine the strength of the connections. Remember those colors, purple, light purple, whatever? It's going in and manipulating them back from full purple back down to light purple, right? And so in a federated model, which I'll show you in a second, all these updates can go to the shared model, right? And then you have, so that could all be done, the model poisoning can be done in brute force through the data, right? Data poisoning would screw the model up, but you can also have programmatically somebody go in and manipulate the parameters programmatically, especially people that have helped design it. So all the partners may have chipped into developing it. So, some people may know information about it. Okay, so this is federated training, right? As you can see, you have the focus data or fine-tuning data for all these different clients, right? And as they go through it, the clients run their data, and then they send the parameters up to a shared server. The shared server has a buffer, and it'll do the parameter averaging. So it's taking all these different parameter updates, it's averaging them, it's recreating the model, it's updating the model, and it sends that model back down to the clients. And so everybody is sharing this information. So this person, this might be Kaiser, this might be Providence, whatever. Kaiser has a huge amount of data, and so Providence could benefit from that. So there's scenarios for this. Decentralized training, again, you're in the fine-tuning stage, but you're in a peer-to-peer arrangement. And the business case for this may be a consortium. It could be people just plugging in for a period of time and getting back out, these type of things. And so the way this works is the model, the parameters are updated to each client. And so if you have a malicious attacker or whatever, and they corrupt those parameters, then they can push that to client after client after client, right? So they can do some serious damage. Supply chain risks. So these are very complex things, right? And they can't necessarily, nobody can build the whole thing on their own. So people reach out for data, they reach out for code, they reach out for a lot of different things. And so you have a lot of different vendors here. For example, there's this thing called Hugging Face. I don't know if anybody's heard, but it's like the GitHub for models, right? And come to find out, I think out of 100 models, they had 99 were corrupted, right? So this happens. But you know what? You can't find, if you go on the internet or whatever, you can't find, you say, give me some examples of breaches in LLMs. Nobody wants to report it. Nobody has to report it, right? And so you don't know what you're getting at this stage in the game. You won't until, NIST steps in and they start pushing security. Purchasing language training data, that's out there. Federated learning service platforms, vulnerable communications, et cetera, et cetera. There's a number of training, testing, security tools that wrap around this during the training period. There's monitoring tools when it's in production. So there's a lot of vendors doing a lot of things in this space. I did a quick scan of all the different vendors. The vendors are over here. Sorry, it's so small. You got potentially 3 or 4 vendors. And this is the functional, right? So these are training products. These are security and training. This is security, et cetera, et cetera. So these products are out there. And conclusion, the training phase is highly vulnerable. Attacks may not be detectable for long periods of time. Models may need to be retrained or if fixable. So if they have a problem and they find it and they need to fix it, they may need to fix it and then retrain the whole model or pieces of the model, depending on how bad it is. If it's very bad, they may have to abandon the model and go and redo everything, right? It's in early stages of this technology, so don't be surprised if that kind of stuff pops up. And so robust mitigation strategies are essential for building secure and reliable LLMs, federated and distributed training configuration. You have to know your partners. You have to trust them because those partners are extending your surface area, right? They're saying, okay, you could attack my partner, but that's also me, right? Because now my surface area has extended over to the vendor. So know your vendors, know your partners. Questions?